we now consider another flow situation for which exact solution of Navier-Stokes equation exists, and that is popularly known as Poiseuille's flow. It's a flow that is developed in a flow in a round pipe. So we call it as Poiseuille's flow, pretty useful. So let us pose the problem. Let us see how the problem is posed before we go after the solution. For this, we consider steady, incompressible, laminar flow of a Newtonian fluid in an infinitely long round pipe of diameter d, or radius, of course, will be half the diameter. We ignore the effects of the gravity. A constant pressure gradient d by p by dx is applied in the x direction. So the pressure gradient, which will be deriving the flow in the x direction, is given by dp by dx equal to p2 minus p1 divided by x2 minus x1. So at x1 the value will be p1 of the pressure, and at x2 the value will be p2. And x1 and x2 are arbitrary locations along the x-axis, but p1 or p2 are applied forcefully. And of course they are attached to the points x1 and x2. Now note that we adopt a modified cylindrical coordinates in this problem, and therefore we will have r theta x, and x is being used instead of z, which is normally used in cylindrical coordinates. We use the coordinates r theta z, but here we use x. It makes no difference really, and therefore the corresponding coordinates will be ur, u theta, and one may write ux or simply u. We derive the expression for the velocity field inside the pipe and estimate the viscous shear force per unit surface area acting on the pipe wall. So the normal things and the same procedures have to be followed that we followed earlier in solving the similar problems. Now here is a pipe vault. You can see cylindrical in nature of its geometry, and that is why we use the coordinates r theta x, and where you can see, since when it comes to the radius of the pipe is r, the x coordinate is taken as the axial line along the center of the pipe, and theta of course will be in the rotational direction not shown here. The density of the fluid is denoted by rho, and the viscosity of the fluid is denoted by mu. So mu is the coefficient of viscosity. Since an external pressure is applied, so it is important to note that at a certain point x1, which is chosen arbitrarily, the value of pressure is P1, and at another point x2, the value of pressure is P2, and they are different. P1 is different from P2. So this geometry explains the problem that is being under consideration. So what are the assumptions for this problem? We list them down as per our practice, or as is traditional, and as we should do, so that we determine the right solution. We don't make a mistake. So although we have this thing in our mind, and normally there are many people who wouldn't take the trouble to write down these things, but it's always useful so that we don't forget something and we take care of all important things. They have implication. They have their own implication. They give rise to boundary conditions that we have to apply when solving the problem and determine the constants of integration and so on. So it's an important part. as far as I am concerned. The pipe is infinitely long in the x direction, that is given in the problem. The flow is steady, so partial derivative with respect to time is gone. They will all be zero. This is a parallel flow, so the r component of the velocity u of r will be zero. The fluid is incompressible, so variation with respect to rho will be zero. Constant pressure gradient, we have mentioned this already. The velocity field is axis symmetric, so no velocity with respect to theta, and therefore u theta is zero, and so will be the partial derivative of all u thetas, all thetas. And we ignore the effect of the gravity. This has been given in the problem. Then we normally go to drawing the picture, the geometry of the problem, that we have already done, and then we go for the assumption and try to determine what boundary conditions are generated by those assumptions. We see that when the radius is equal to r, r is the capital R is the radius of the pipe under consideration, while small r is a variable that moves from 0 to capital R. So at r, the velocity v is equal to 0. Again, why? Because of the viscosity, what we call as no slip condition. The second boundary condition comes from the fact that the central line of the pipe is in excess of symmetry. So therefore, at r equal to 0, partial derivative of u with respect to r is 0. Trying to determine these values, substituting the value from the continuity equation written in cylindrical coordinates, we obtain only this value, because u of r is 0, u theta is 0, so they don't contribute anything in the continuity equation, and the only non-zero term is this one. And this is what we have to solve. We call it as equation 2. Since u is varying only with respect to r, the other variation with respect to theta and xr is not there. Therefore, u will be only u of r.